Hello everyone, in this video we are going to continue our discussion on 1D elements. In the previous video we talked about bar elements, now we are going to introduce trusses. So similar to bar elements, trusses are one-dimensional, which means that the nodal variable depend only on one dimension towards the direction of the member. Truss members could be either in tension or compression. So in this example that I'm showing you, we have two members that are in compression and one member in tension. The main difference between bar and truss is that the members are spread out in a 2-dimension or 3-dimension for 3D trusses. And in a global coordinate, each node can have multiple degrees of freedom. But because they are still 1D, each degree of freedom depends on one direction. We have two main categories of trusses, the ones that are statically determinate or the ones that are indeterminate. And the definition is that if the number of unknown reactions are as many as the equilibrium equation that we have, we can determine the unknowns statically. But for indeterminate trusses, the number of unknown reactions, for example, for this problem, there are 4, are more than the equilibrium equation that we can write in 2 dimensions. So they are statically indeterminate. And we use some strength of material rules to find the 4th unknown because we need additional equation if you want to solve additional unknowns. Finite element can handle both categories, and that's one of the advantages of using FEA to solve truss problems. Our first task in any FEA approach for any element is find a stiffness matrix, finding the global stiffness matrix. But we have to start with local stiffness matrix, which means that the stiffness matrix that belongs to each member or element. Here I'm showing you a free body diagram of a truss member. There are forces applied, and forces are equivalent to a stiffness times deformation. And if you wanna, and this member is in compression, if you wanna show the forces along positive x, so I just need to flip the order here, and I can show it k uj minus ui. And this is the force for one node. If I want to show it for the whole element, I have to show it in a matrix form. So this is the stiffness matrix for the whole element. You can see that the stiffness matrix, unlike bar element, is 4x4 instead of 2x2. That's because we have 2 degrees of freedom at each node, uix and uyy. The displacement of node I in x direction and the displacement of node I in y direction, and same thing for the second node. Here, because I'm showing you an element which is in 0 degrees, so we don't have any displacement in y, so these 2 rows are 0. But in general, our matrix, our stiffness matrix is 4x4, and we have 4 degrees of freedom in total. It's much easier to work in local coordinate, but because members have different angles, therefore we are going to have multiple local coordinates. So we have to transfer our local coordinates into one single global coordinate so we can form our equation. That's why we need to find a relation between local and global coordinates. So here in this example, for this member, we have the local coordinate x towards the member and y perpendicular to that. And then we have the global coordinate. Here is based on the displacement. uix, the small u, indicates the local displacement, and the capital U indicates the displacement in global coordinate. Same thing for forces. We can represent forces in local and global coordinates. So here, if we want to find the relation between the displacement in global and local, we have to use a transformation matrix. We call that transformation matrix T theta, because the transformation depends on the angle of transformation and is defined as cosine theta, sine theta, negative sine theta, cosine theta. And that's for displacement of a node I, transferring it from global coordinate into local coordinate. And if I want to write it for the whole element, which means that if I want to write it for two nodes, I just need to write the transformation matrix again here. So in my 4x4 matrix, I place two transformation matrices. And that's the total transformation matrix for my element. 4 degrees of freedom here in global coordinate, 4 degrees of freedom in local coordinate, and this is the transformation that if I have one of them, I could find the other one. So I could relate the displacement in local to global coordinate. The transformation for force is identical. I mean, for transformation metric, it doesn't matter what variable you are transforming. So here we're just writing the transformation matrix for forces as well. Here is for the nodal transformation matrix. Each node has 2 degrees of freedom. And here is for the whole element, 4 degrees of freedom. So it's identical to displacement. It's just the symbol is force. Here as an exercise, if we know that the transformation between the global and local is, we are using the transformation matrix T theta. What if we want to transform the local to global? So the other way around, instead of using the global displacements and transfer it to the local, what if we want to do the opposite? What would be the transformation? So as you have probably correctly guessed, we are going in the opposite direction. We are going from the local to global. So we just need to plug negative theta here. So in our transformation matrix, we can simply plug negative theta. Or if you're just going to look at it mathematically, if you have a transformation matrix, now if you want to go the opposite way, that would be the inverse of transformation matrix. Comparing these two, that tells us the inverse of transformation matrix, or if we use negative theta, the result will be the same. Also, additionally, the transpose of the transformation matrix is the same as the inverse of transformation matrix. That makes it simpler for us to find the inverse. It's much easier to find the transpose. Such matrices are called or referred to as orthogonal matrices whenever the transformation, the inverse and the transpose are the same. So now that we know how to find the inverse, so as an exercise, what would be the inverse of this transformation matrix? We don't need to take an inverse. We just concluded that the transpose is the same as inverse for the transformation matrix. And the transpose, which means that the first row would be the first column. And here again, the first row, the second row would be the second column. So you're changing the rows and columns. Now we are going to find the relation between global displacements and global forces. You can prove this relation. It's very straightforward. If you just write the relation between the local and global displacements and also local and global forces, and we know the relation between force and displacement are related by the stiffness matrix, you can come up with this equation. So in this equation, in this equation, K is the stiffness matrix of our element that has two nodes in the local coordinates. So if we simplify that, that would be our stiffness matrix in global coordinate. And then here we represent cosine and sine by C and SS to make it simplified. So here we are relating the displacement in global coordinate to the forces in global coordinate. We mentioned that we like global coordinate because it's unique for all our members. And if you're gonna add stiffness matrices or have any transformation or addition, all stiffness matrices need to be in the same coordinate. That's why our first task is to write our stiffness matrix in global coordinate. Here we're gonna talk about the procedure using an example. So in this example, we're gonna find the stresses in each member of this truss. We have two external loads, 500 pounds, two 500 pounds being applied to node 4 and node 5, and then we have boundary condition at node 3 and node 1. These are simply supported. So we have technically 4 unknowns. So in this truss, we have 1, 2, 3, 4, 5 nodes, and then we have 1, 2, 3, 4, 5, 6 elements. So in bar elements, the number of elements were less than the number of nodes. But here, the number of elements are more than the number of nodes because each node can connect multiple elements. So we want to find reaction forces, we want to find forces in each member, and then stresses in each member. One important step in solving truss problems using FEA is to have the node connectivity. So here for element 1, we know element 1 is connecting node 1 and node 2. Each element has 2 nodes. Element 2 is connecting node 2 and 3, and then same thing for others. When you come to element 5, you can see it's connecting node 2 and 5. So it's not a specific order saying that node 5 is connecting, element 5 is connecting node 5 and 6. We need to have this node connectivity to be able to solve the problem, and that's given to us by the problem statement. So in your program, in your Excel file, you need to write this node connectivity, and each element is at an angle. Some of them are at 0, some of them are perpendicular, and then we have 2 that are 135 and 45. So element 1, 3, and 6, the angle is 0, and this is the node connectivity connecting 1 to 2, 3 to 4, and 4 to 5. Element 4 is at 90 degrees, and you can see the local coordinate here and global coordinate on top of each other. Here the local coordinate and global coordinates make a 90-degree angle. For element 2, it's at 135, and the angle is measured from positive x going counterclockwise. And our local coordinate, the positive x is going from the lower number to a higher number. Same thing here, 2 to 5 is 45 degrees. So here I'm showing you the information about each element. For all elements, the elastic modulus and the area is the same. That's the case for most problems, but it doesn't have to be. If they are different, we have to add another column here. In this column, the values are going to be different if A was different. So we have the element, what nodes are each element is connecting, the length. So if we have the coordinate of each node, we can find the length because the coordinates are given in Cartesian coordinate, and in Cartesian coordinates x and y are perpendicular. So we can use Pythagorean theorem to find the length based on the coordinate. And the elastic modulus is the same, and the angle for each element. So this table is giving us all the information that we need to solve the problem, and this is done in Excel. So I need to find the element stiffness in global coordinate. So the terminology is very important. In trusses, we have local coordinate, global coordinate, but also local stiffness and global stiffness. So here is the local stiffness matrix in global coordinate. We are still talking about one element, so that's local stiffness. If we are talking about the stiffness matrix of the whole system, then that's the global stiffness matrix. So here, while we are still in global coordinate, but we are writing for just element 1, AE over L, and the corresponding angles. Here, this cell is highlighted. You can see the equation. That would be cosine, radians, because the angle is easier to find in angles. In degrees, we find it in degrees and then change it to radians. That's the function requirement of cosine function in Excel, and then a squared. So we are describing this component. So we can find a stiffness matrix for our member 1. And here are the other local stiffness matrices for other members. Member 2, 3, 2, 6. And each member have the same A and E. That's why there is no indices here, but the lengths are different. So they are divided by the corresponding lengths. But once we found the stiffness matrix for each member, we need to find a global stiffness matrix, the stiffness matrix for the whole system. But the step before that, similar to bar elements, is to find it in a global form. In a global form, our system has 10 degrees of freedom. Has 5 nodes. Each node has 2 degrees of freedom, so we have 10 degrees of freedom, which means that our stiffness matrix in global form would be 10 by 10. Here we are gonna show as a practice the stiffness matrix in a global form for element 5. Element 5 is 45 degrees. This is the equation for stiffness matrix in global form or in global coordinate. If I place 45 degree, because that's the angle of element 5, that's what I find here. I'm showing it with different colors. I'm gonna tell you why they are in different colors. And this is the multiplication that we always have, AE over L5. L5 means the length of member 5. Now I have to place this local stiffness matrix in a global form. In a global form, my matrix is 10 by 10. So you can see how I place it. The red goes here, the green, so they are color coded. So my element 5 is connecting node 2 and node 5. And that's what this relationship is about. This is what the stiffness matrix forces in 2 with the displacement in node 2. Forces in element in node 2 with displacement in node 5. But when we are writing in global, we are writing for all nodes from 1 to 5, from 1 to 5. So we need to know where to place it. Here, the first part is relating forces in 2 with displacement in node 2. So we're going to place it in the corresponding location in the third and fourth column and third and fourth rows, because they are also relating the forces in node 2 with the displacements on node 2. Similar approach for between node 5 and node displacement at node 5 with the forces of node 2 and so forth. So we have carefully placed our local stiffness matrix in global form. When they are placed in a global form, then we can add the local stiffness matrices together to form our global stiffness matrix. So we do the same thing for the first element, the second, the third, the fourth. I showed you the fifth one and the sixth. And now that all of them are in global form, then they can be added together, because all of them would refer to the same thing. The first one, the first column is relating the first, the displacement of node 1 and the fourth at node 1. So we have the same terminology for all of them, so we can add them together. Now that we have the stiffness matrix in global form, and this is the global stiffness matrix, this is the stiffness matrix for the whole system, then the approach would be the same as we talk for bar elements. In FEA, all our effort is to find the stiffness matrix. Once we find it, then the rest is the same. So from now on, I'm going to talk about the same thing that I talked for bar elements, applying boundary condition and load. Here, let's start with our boundary condition, our displacement. We know here is pinned, so there is no displacement in x or y direction. Here is the same, no displacement in x or y direction. So u1x, u1y would be 0, then u3x and u3y would be 0. So my modified displacement matrix after applying the boundary condition would look like this. These components would be 0. Same thing for forces. For forces, we have external forces and also reaction forces. Now I'm going to write all of them together, but later on you will see I will separate external forces from reaction forces. They need to be treated differently in our analysis, and that's a very important step. Well, for now, let's see. Whenever we have information about the displacement, whenever we say the displacement here is 0, that means that we have a reaction force. Same thing for here. So we have reaction force at 1, F1x and F1y. We have reaction forces at node 3 for x and y. And also at node 4y, we have external load. At node 5, we have also external load. And so after I plug in the values, this would be on my modified force matrix. Remember, we are talking about external forces. Each member is going to have internal forces. But here, we're talking about external forces. Now I'm going to apply boundary condition to my stiffness matrix. So we talked about boundary condition to modify our force and displacement matrix, but I'm going to apply it to my stiffness matrix. If you remember, in bar elements, we said that we cannot have unknown on both sides of equation. The nodal displacements are unknown. I do not like to have reaction forces here. Then I would have unknowns on both sides. So what I'm going to do, I'm going to remove the rows and columns that include the reaction forces, and I will find the reaction forces later. If the reaction forces are known, then they would be external loads, and then they would be fine. You could keep them. But if they are unknown, you're going to remove them. So for that reason, I'm going to remove the first 2 rows, and also the rows associated with the reaction forces of node 3, then the corresponding column, the first 2 columns, and the 5th and 6th columns. So now from 10 by 10, I've reduced my stiffness matrix to 6 by 6. So that's the first approach. Now I can find the nodal displacements. F equals Ku. So U, the nodal displacement, would be inverse of my stiffness matrix times F. If I find the inverse of my stiffness matrix times F, my external forces, I can find the nodal displacement. Remember, these nodal displacements are in global coordinate. And if you want to find the stresses or force in each member, we need to convert it back into a local coordinate using a transformation matrix. But before that, let's not forget about the reaction forces that we have. We said that to find the reaction forces, we are going to separate them from external load. So F, we are going to say that F plus R, which are the external loads. Here are the loads that we don't know. And R, therefore, if I take F to the other side, would be Ku minus F. So now I found nodal displacement, so it's not unknown. So everything is known on this side. The nodal displacement are known. The external loads are known, so I can find the reaction force. So this is K, U minus F gives me the reaction forces. So you can see this also came out as 0, the reaction force of node 1 in y direction. So I found the 3 reaction forces that I needed. So far I found all the nodal displacement in global coordinates, also all the reaction forces. If you want to find the forces in each member, we know the equation is the stiffness simply times the deformation. For node 1 is the difference between displacement of node 1 and node 2. For element 5 is between node 2 and node 5. But these are in local coordinate. If you want to find it based on global coordinate, we are going to use the transformation matrix again. Here are the global displacements that we found earlier. and we are going to find the local displacement. Here I'm just showing you for element 1. That's why it's just 4 by 4. Element 1, the local coordinate and global coordinate are on top of each other. So that's why the nodal displacement in local coordinate would be exactly the same as the global coordinate if you look at here. But for other nodes, you have to use this transformation matrix to transform your displacements in global coordinate to local coordinate. If you want to find the stress and the strains, we have the forces. So stresses are just the force divided by the area. I have the area here are cancelled out. So that gives me my stresses. And strains are, well, that's an error in this equation, but it's stresses divided by E. So that gives me the strains, which is deformation by the original length. For failure analysis, we have two different modes of failure. Our members are either in tension or compression. That means that our elements could yield or they could buckle if they are in compression. So we have to take into account both modes of failure. So for yielding, we know the stresses. We have to compare it with the yield strength of our material and then find a safety factor. NK means the safety factor of member K, because each member is going to have a different safety factor because they have different stresses. If they are all made of the same material, that means that some members are likely to fail first than the other ones. This is based on yield. And for buckling, we know for a simply supported column, that's the equation that we use. P critical of member K, the critical load that the member can have before it buckles. And it's pin because each member is pinned on both sides. So we can treat it as a simply supported. Pi squared EI over LK, which is the length of the element squared. And if I want to include the safety factor, I'm going to compare the internal load of each member with the critical load that it can handle. And then come up with a safety factor here as well. Remember that depth buckling is only applicable to if the member is in compression. So you should check only the members that are in compression. For those members, you find two safety factors. And whichever is smaller is going to determine the mode of failure. Whether your member is going to fail in buckling mode or yield. In 3D, the approach is the same. Instead of just having 2 degrees of freedom per node, we have 3 degrees of freedom per node, both in local and global coordinate. And you can see in 3D we use 3 angles. 2 of them are independent. The third one can be obtained if we have the other 2. The stiffness matrix for 3D trusses take this form. You can see that we have it's a 6 by 6 matrix because each element has 6 degrees of freedom. We have 3 degrees of freedom at node I and 3 degrees of freedom at node J. But the rest would be the same. Our approach would be the same. Finding the local stiffness matrix, finding the local stiffness matrix in global coordinate, finding the global stiffness matrix and applying boundary condition and finding the solution. Some of the helpful Excel function that you can use is matrix multiplication, M, matrix multiplication, matrix inversion, M inverse, radians, if you want to change degree to radian. But my preference is Matlab is more powerful. You could do a lot more with Matlab. So I've shown you this before. You have to remove your rows and columns, so that would be a helpful function. And remember to remove your rows if you need to remove multiple rows at the same time, because if you remove the second row and then the third row, the new third row is actually the fourth row of the original matrix. and or here you're telling that remove all the rows and columns that you have to. So I usually assign my boundary condition. Whenever it's 0, it means that my boundary condition is 0, and whenever it's not 0, I just say 1. That means that I don't have any boundary condition. And I tell my stiffness matrix to remove wherever you have to remove, whenever we have a boundary condition here. So it automatically removes the corresponding rows and columns. This is for rows, you have to write it for column, whenever the matrix B is 0. So you technically just assign your boundary condition and your code will take care of that. There are multiple ways to do it. This is just some suggestions that I'm giving you here. An important thing here is when you want to find the nodal displacement, you can use inverse of k times f, or k backslash f. That uses a Gaussian approach, which is not intuitive. You would think that you should divide f k, not kf, but that's a Gaussian approach, and it's a backslash, it's not slash. And it's always helpful to pre-allocate your stiffness matrix for efficiency purposes.